3 minutes after the Big Bang, it was over, not the explosion, the synthesis. In 180 seconds, the universe produced its entire supply of hydrogen and helium, 3/4 of one, 1/4 of the other, a ratio predicted by theory to a fraction of a percent and confirmed by observations of the oldest gas clouds. 3 minutes. The chemical composition of the cosmos settled. This is the story of how the universe cooled. It sounds like a small story. It isn't. Everything we are, every atom in our bodies, every galaxy we can see, and probably the reason there is anything at all rather than nothing, came directly out of the first few minutes of that cooling process. The universe's entire chemical inventory was decided before it was 3 minutes old. The ratio of hydrogen to helium in every star that has ever burned was set before any star existed. The number of neutrino species, the neutron lifetime, the strength of the weak nuclear force, none of these things were chosen by astronomers. They were measured after the fact by looking at consequences that played out in those first minutes and that left permanent marks on the universe we can read today. The structure of everything that followed, galaxies, stars, planets, the long chain of chemistry and biology was not shaped primarily by anything that happened in the last 13 billion years. It was set up in those first 3 minutes, understanding how and why and what might have been different. That is what we are here to do. To understand what we are actually talking about, we need to build a picture. Not a metaphor, a real physical picture of what it means for space to expand. Imagine you draw 2 dots on the surface of a balloon, now inflated. The dots don't move across the surface. They don't push off from each other like billiard balls. The surface itself grows. The space between the dots increases, and neither dot is the source of that increase. Neither dot is the center. Every dot sees every other dot receding from it. And the farther away the dot, the faster it seems to recede. Not because it's moving faster in any absolute sense, but simply because there is more rubber between them. This is exactly what our universe does. And the critical number that describes its size at any moment is called the scale factor. Call it A. It's not an absolute distance. It's a ratio, a measure of how much all cosmic distances have stretched compared to some reference moment we choose to call now. If A doubles, all distances double. If A was 1,000th of its current value, then a galaxy that today sits 1 billion light-years away was then only 1 million light-years distant. The positions of galaxies on large scales don't change. The space between them does. The rate at which it changes with time, divided by A itself, is called the Hubble parameter, or evaluated at the present moment, the Hubble constant. It describes the fractional rate of expansion, not how fast space is growing in absolute terms, but how fast it is growing relative to how big it already is. Edwin Hubble measured it observationally in 1929 by looking at distant galaxies and finding that their light was systematically shifted toward the red end of the spectrum, and that this shift was proportional to their distance. The farther the galaxy, the redder its light. The natural interpretation was that these galaxies were flying away from us, but that's not quite what is happening. The space between us and them is stretching, and as it stretches, the light traveling through it stretches too, its wavelength increasing, its frequency dropping, its energy falling. This is the cosmological redshift, and it is not the same thing as the Doppler effect, even though for nearby galaxies, the two are mathematically indistinguishable. For very distant objects, light can be redshifted by factors of 10 or 100 or 1,000, while the source was at the moment it emitted that light already receding from us faster than light. That's allowed because what's moving faster than light is not the galaxy, it's space itself. The speed limit of special relativity applies to objects moving through space, not to the expansion of space. This is not a loophole or a technicality. It has real, measurable consequences. There are objects we can see today that were, at the moment they emitted the light we're now receiving, already moving away from us faster than light. The light they sent was like a message dispatched upstream against a current stronger than the messenger, and yet it eventually reached us, because the expansion rate was decelerating over cosmic time, and eventually the current slowed enough that the light could gain ground. We are currently receiving photons that spent 13 billion years in transit across a gap that was actively widening the entire time. The observable universe extends not 13 billion light-years in every direction, as you might naively expect from its age, but 46 billion light-years. The expansion contributed those extra 33 billion light-years of reach. Cosmologists use the redshift as a clock. If a galaxy's light has been stretched to twice its original wavelength, the scale factor was half its current value when that light was emitted, and we say the galaxy has a redshift of 1. Redshift 3 means the scale factor was 1/4 its current value. Redshift 1000 roughly marks the moment when the universe first became transparent to light. Before that, matter and radiation were so tightly coupled that photons couldn't travel freely. That is the surface of last scattering, the origin of the cosmic microwave background. The redshift is a compact, precise way to talk about cosmic time without committing to a specific cosmological model. Now, here is the key connection to temperature. If stretching space redshifts light, if it lowers the frequency and energy of every photon traveling through it, then it also cools the radiation bath. Temperature, at its root, is average energy per particle. As the universe expands and photon wavelengths stretch, the average photon energy falls. The temperature drops in exact proportion to the scale factor. Double the size of the universe, halve the temperature. Run this backward, compress the universe to 1,000th of its current size, and the temperature was 1,000 times higher. Compress it to 1/1000th, and the temperature was 1,000,000,000 times higher, around 3 trillion degrees, or a few hundred million electron volts. That is where we will spend most of our time today. The framework that makes all of this precise was worked out by Alexander Friedmann in 1922. He was a Russian mathematician who had taught himself general relativity after the war and applied it to the universe as a whole. Einstein initially dismissed his derivation as containing a mathematical error, then rechecked it and wrote a brief note admitting that the calculation was correct and the results were physically valid. Friedmann died of typhoid 3 years later, at 37, without seeing any of his cosmological predictions confirmed. What Friedmann found was that Einstein's equations, applied to a spatially uniform universe, reduced to a pair of much simpler equations that describe how the scale factor evolves over time. They are called the Friedmann equations, and they do something remarkable. They connect the geometry of space to the physical contents of the universe in a direct, calculable way. General relativity does not assume that space is flat. It allows space to be positively curved, curving back on itself like the surface of a sphere, so that traveling far enough in any direction eventually brings you back to where you started. It allows space to be negatively curved, like an infinite saddle where parallel lines diverge. Or it allows space to be exactly flat, extending infinitely without any curvature at all. Which of these geometries actually describes our universe depends on how much matter and energy it contains. A universe with more than a critical density of content is positively curved. Less than critical, and it's negatively curved. Exactly critical density means exactly flat. Every measurement we can make today, from the cosmic microwave background to the large-scale distribution of galaxies, tells us that our universe is, within experimental precision, exactly flat. This is remarkable. The initial conditions of the universe would have had to be tuned to extraordinary precision to produce flatness today. Any deviation from flatness in the early universe grows over time, not shrinks. If the universe was flat now, it must have been even more precisely flat in the past. At 1 second after the Big Bang, the density would have had to equal the critical density to within 1 part in 10 to the 15th. This is one of the puzzles that inflation resolves by providing a physical mechanism that drives the geometry toward flatness regardless of the starting point. In a flat universe, the Friedman equations tell us that the expansion history is entirely determined by three competing components, each of which dilutes at a different rate. There is radiation, photons, and any particles moving close to the speed of light, including neutrinos in the early universe. There is matter, both the ordinary baryonic matter that makes up atoms and the dark matter we cannot see, both of which are slow and cold on cosmological scales. And there is vacuum energy, the energy density of empty space itself, associated with Einstein's cosmological constant, now reinterpreted as the quantum mechanical zero-point energy of the vacuum. Radiation dilutes fastest. As the scale factor grows, radiation energy density falls as the fourth power. One factor of a cubed for the expanding volume, one more factor of A for the redshifting of each photon's energy. Matter falls only as a cubed. It spreads through a growing volume, but each particle retains its rest mass energy. Vacuum energy doesn't fall at all. More space means more vacuum, so the total increases, but the density, energy per unit volume, stays constant. The consequence is clear. In a very young, very small, very dense universe, radiation must have dominated. As the universe grew and radiation density fell fastest, matter eventually took over. And as matter diluted while vacuum energy held steady, vacuum energy eventually came to dominate. The three eras, radiation domination, matter domination, dark energy domination, are not a theoretical construct. They are a direct consequence of these different dilution rates, and the transitions between them happened at specific, calculable moments that we can identify in observations. Each era produced a different kind of expansion. During radiation domination, the scale factor grew as the square root of time, expansion decelerating because the universe's energy density was large enough to slow the growth. During matter domination, the scale factor grew as time to the 2/3 power, still decelerating but more slowly. During dark energy domination, the scale factor grows exponentially. The universe transitions from deceleration to acceleration, and the expansion rate climbs monotonically from that point on. The transition from radiation to matter domination happened when the universe was about 50,000 years old, at a temperature of roughly 10,000 electron volts. At that moment, the universe was still opaque. Photons and matter were still tightly coupled, and the acoustic oscillations that would later be frozen into the CMB were still propagating. The transition to matter domination changed the dynamics of those oscillations and left an imprint on the CMB power spectrum that we measure today. The transition from matter to dark energy domination happened about 6 billion years ago, coincidentally, approximately when our solar system was forming. At that point, the universe switched from decelerating to accelerating. The switch was first detected in 1998 by two independent teams, the Supernova Cosmology Project and the High-Z Supernova team, who were using Type Ia supernovae as standard candles to measure the expansion history. They found that distant supernovae were about 20% fainter than expected in a matter-dominated universe without dark energy. The universe had been expanding more slowly in the past and is now accelerating. This result, shared by Saul Perlmutter, Brian Schmidt, and Adam Rees, earned the 2011 Nobel Prize in Physics. We live today in the early phase of the dark energy era. The expansion is accelerating, and it will continue to do so forever, unless dark energy is not a cosmological constant, but something more dynamical, a field whose strength evolves with time. Future surveys are designed to distinguish between a true constant and a slowly varying component. If dark energy is a constant, it will drive the universe into an endless de Sitter expansion, gradually isolating our local group of galaxies as the rest of the universe recedes beyond the horizon. Galaxies more than about 5 billion light-years away are already receding faster than light. Galaxies beyond about 60 billion light-years will never be reachable by any signal we send today. The universe is not just expanding, it is becoming less knowable. But none of this addresses the early universe. We need to go back much further than 50,000 years. We need to go back to fractions of a second. After inflation, the period of exponential expansion that preceded the hot Big Bang, the universe underwent a process called reheating. The field that drove inflation, called the inflaton, had been rolling slowly toward the minimum of its potential energy, like a ball on a very gently sloping hillside. During this slow roll, its energy density was nearly constant, producing a near-constant Hubble parameter and near-exponential expansion. This was inflation. When the inflaton reached the bottom of its potential and began to oscillate, it radiated energy into all the other fields of nature it was coupled to, producing a hot, dense plasma of particles and radiation. This is the Big Bang, not a singularity, but a physical reheating process with a temperature that can be calculated from the model of inflation. Typical estimates range from 10 to the 8th to 10 to the 16th electron volts, depending on the specific inflationary model. To understand why inflation was a necessary idea, it helps to appreciate just how mysterious the hot Big Bang model was without it. Consider 2 points on opposite sides of the sky, separated by 180 degrees. Their light is just now reaching us. We are receiving it for the first time, after traveling for 13.8 billion years. Those 2 points are just now entering our cosmic horizon. They have never been in causal contact with each other. No signal has ever traveled between them, and yet they have exactly the same temperature, measured to 1 part in 100,000. If they have never interacted, how did they equilibrate to the same temperature? The best explanation available before inflation was, they simply started that way. Which is not an explanation at all. It is a statement of the problem. Inflation dissolves the puzzle. The exponential expansion stretched a tiny, causally connected region to a size far larger than the observable universe. Every point we can see was once in intimate causal contact with every other point we can see. They equilibrated then. The thermal uniformity we observe today is not a mystery requiring special initial conditions. It is the natural outcome of having been in contact. The same inflation that stretched the region to cosmic size also amplified quantum mechanical fluctuations to macroscopic scales. Quantum mechanics does not allow the inflaton field to be perfectly uniform. Heisenberg's uncertainty principle guarantees tiny fluctuations on all scales. During inflation, these fluctuations were stretched to wavelengths far larger than the Hubble radius. They were frozen outside the causal horizon, unable to evolve. When inflation ended and the universe reheated, these frozen fluctuations re-entered the horizon and appeared as slight variations in energy density. One region was a fraction of a percent denser than average, another a fraction of a percent less dense. These were the seeds of structure. Gravity amplified them over 13 billion years, pulling matter toward the overdense regions, creating the cosmic web of filaments and voids and clusters that we observe in galaxy surveys today. These predictions can be tested with precision. The simplest inflation models predict a nearly scale-invariant spectrum of initial density fluctuations, roughly the same amplitude at all scales, with a slight tilt toward larger amplitudes at longer wavelengths. They predict that the fluctuations are Gaussian distributed, without significant deviation toward asymmetry or non-Gaussianity. They predict a specific relationship between the amplitudes of density fluctuations and gravitational wave fluctuations, parametrized by the tensor-to-scalar ratio. The cosmic microwave background satellites WMAP and Planck have measured the fluctuation spectrum with extraordinary precision. The spectrum is nearly scale invariant, with exactly the predicted slight tilt. The fluctuations are Gaussian. The tensor-to-scalar ratio has not yet been measured. Gravitational waves from inflation, if present, are at an amplitude just below current sensitivity, but upper bounds are consistent with the simplest models. Inflation is not yet a settled theory. There are hundreds of specific models, ranging from the elegant to the contrived, all broadly consistent with current observations but making predictions that diverge in their details. Distinguishing between them requires measuring the tensor-to-scalar ratio, pinning down the spectral tilt to higher precision, and searching for signatures of non-Gaussiacity. Future CMB experiments and 21-centimeter surveys of the hydrogen distribution in the early universe are aiming at exactly these measurements. Inflation is the leading paradigm, with strong observational support, but it remains an unfinished story. After reheating, the universe was filled with a quark-gluon plasma. This is a state of matter with no analog in everyday experience, and understanding it requires confronting the strange behavior of the strong nuclear force. The strong force is what holds protons and neutrons together. More precisely, it holds the quarks inside them together. A proton is made of 3 quarks bound by exchanging particles called gluons. In ordinary conditions, quarks are permanently confined. You cannot extract a single free quark from a proton. Try to pull one away, and the energy stored in the stretching color field creates new quark-antiquark pairs from the vacuum, and you end up with new hadrons rather than a free quark. The analogy sometimes used is a rubber band. Stretching a rubber band stores energy, and if you stretch it far enough, it snaps. But when a color field snaps, it doesn't break. It creates new particles from its stored energy. There is no way to get a free quark, no matter how much energy you apply. The strong force has another unusual property. It grows weaker at shorter distances, not stronger. At the scale of a proton, the coupling is large, and the force is strong. At much shorter scales, at distances probed by the highest energy colliders, the coupling is small, and quarks behave almost as free particles. This phenomenon is called asymptotic freedom, discovered by David Gross, Frank Wilczek, and David Pulitzer in 1973, for which they received the Nobel Prize in 2004. Asymptotic freedom is why the quark-gluon plasma forms at high temperatures. When the temperature is very high, the typical quark-quark distance is very short, proportional to the inverse temperature, and at short distances, the strong coupling is weak. The quarks behave quasi-freely, screening each other's color charges through the dense medium. Confinement breaks down. Particle accelerators at CERN and at the relativistic heavy ion collider in New York recreate the quark-gluon plasma by colliding heavy nuclei, lead at CERN, gold at Arctic, at nearly the speed of light. The 2 nuclei, each containing hundreds of protons and neutrons, pass through each other in a fraction of a femtosecond, and the collision deposits enough energy to melt the nuclear matter into a droplet of quark-gluon plasma. This droplet lasts perhaps 10 to the minus 22 seconds, about the time it takes light to cross a proton, before it expands, cools, and hadronizes back into ordinary particles. This is long enough to be characterized. The quark-gluon plasma turns out to behave not like a weakly interacting gas, as theorists initially expected, but like an almost perfect liquid, a fluid with extraordinarily low viscosity, far lower than water, lower than any previously measured fluid. It flows collectively, responding to pressure gradients on scales smaller than a nucleus. The spatial geometry of the collision, its initial asymmetry, is imprinted in the final angular distribution of the particles produced, and this angular pattern matches hydrodynamic predictions assuming near-zero viscosity. The early universe, in its first microsecond, was the most perfect, lowest viscosity liquid ever to exist. The nature of the transition from quark-gluon plasma to ordinary hadronic matter is itself an active research area. Unlike the electroweak transition, the QCD transition at around 170 million electron volts cannot be studied using perturbation theory. The strong coupling is large at this temperature scale, and standard approximation methods fail. It requires numerical simulations on supercomputers, a field called lattice QCD, in which the continuous four-dimensional spacetime of the theory is replaced by a discrete grid, and the field equations are solved numerically. These simulations show that the transition for physical quark masses is not a sharp first-order transition, but a smooth crossover. the universe passed through it without drama, no bubble nucleation, no latent heat, just a rapid change in the character of the dominant degrees of freedom over a temperature range of a few tens of millions of electron volts. Now we need to address something that should bother anyone who has thought carefully about the physics. If matter and antimatter are produced in exactly equal amounts when energy converts into particles, which every laboratory experiment confirms, then the universe immediately after reheating should have contained equal numbers of quarks and antiquarks. As it cooled, they should have annihilated each other completely. What should remain is a universe of pure radiation, photons carrying the energy of the annihilated pairs. But no matter, no protons, no atoms, no galaxies, no us. This is not what happened. But understanding why requires confronting one of the deepest unsolved problems in physics. For every 3 billion photons in the universe today, there is exactly one proton. 3 billion antiprotons annihilated with 3 billion protons. 1 proton per 3 billion survived. The excess was not random noise. It was a systematic imbalance, present everywhere in the observable universe. Every atom you have ever touched, every planet you can name, every star in every galaxy is made of matter. There is no antimatter galaxy on the other side of the universe keeping the books balanced. The imbalance is absolute, or nearly so. In 1967, Andrei Sakharov, a physicist who would later become a dissident and Nobel Peace Prize laureate, identified the 3 conditions any physical process must satisfy in order to generate this imbalance from symmetric initial conditions. First, there must be violation of baryon number conservation. Baryon number is the count of protons plus neutrons minus antiprotons minus antineutrons. In known physics, this number is always conserved. You cannot create or destroy a proton without simultaneously creating or destroying either another proton or an antiproton. But if baryon number is strictly conserved, the universe will always have the same number of particles and antiparticles it started with. To generate an asymmetry from nothing, there must be processes that violate this conservation. Second, there must be violation of CP symmetry, the combined symmetry of charge conjugation and parity reflection. Charge conjugation replaces every particle with its antiparticle. Parity reflection mirrors all spatial coordinates. Together, CP symmetry says that if you take a physical process and replace all particles with antiparticles while reflecting space, the result should be equally likely. If CP is exact, particle processes and antiparticle processes occur at identical rates, and no net asymmetry accumulates. CP violation has been observed directly in the decays of certain mesons and in neutral kaon oscillations. It exists, but the amount observed in the standard model is far too small to account for the observed matter-antimatter asymmetry. There must be additional sources of CP violation in physics beyond the standard model. Third, the universe must be out of thermal equilibrium. At perfect equilibrium, every forward reaction is precisely balanced by the reverse reaction. Any asymmetry generated in one direction is immediately washed out by the reverse process. The expansion of the universe itself provides out-of-equilibrium conditions. The Hubble rate acts as a clock that can run faster than certain reaction rates, freezing the system before it can equilibrate. All 3 conditions are, in principle, satisfiable. The question is which specific physical process actually generated the asymmetry. There are dozens of viable mechanisms. The simplest to describe involves grand unified theories, frameworks that unify the strong force with the electroweak force at temperatures around 10 to the 16th electron volts. In such theories, there exist massive particles, sometimes called X-bosons, that mediate transitions between quarks and leptons, processes normally forbidden in the standard model. These particles can decay through multiple channels, some producing quarks and leptons. If CP is violated, the rates for the particle and antiparticle decay channels differ slightly. Integrate over all the decays as the universe cools through the temperature where X-bosons become unstable, and you accumulate a net excess of quarks. 1 part in 10 billion, everything else annihilates. The problem with this scenario is that it requires temperatures potentially above the reheating temperature of some inflation models, and it may never have been reached. A more experimentally accessible scenario is electroweak baryogenesis, which operates at temperatures around 100 electron volts during the electroweak phase transition. We will return to this shortly. There is also a mechanism called leptogenesis, in which the asymmetry is first generated in the lepton sector as an asymmetry between neutrinos and antineutrinos, and then partially transferred to the baryon sector through processes active at high temperatures. Leptogenesis is attractive because it naturally connects to the physics of neutrino masses, which we know from oscillation experiments must be non-zero. The honest answer is that we do not know which mechanism is correct. We may never be able to test grand, unified theories directly. Leptogenesis involves heavy, sterile neutrinos that may be unreachable. Electroweak baryogenesis depends on the strength of the electroweak phase transition, which current Higgs measurements are beginning to constrain. The situation is tantalizing. The asymmetry is measured with precision. Its origin is unknown, and narrowing down the possibilities requires experiments at the frontier of particle physics. There is one more thread worth pulling. If the CP violation that generated the asymmetry arose through a mechanism involving spontaneous symmetry breaking, a mechanism that could in principle have gone either way, then different regions of the early universe might have developed excess matter or excess antimatter independently. Our observable universe is all matter. But beyond the cosmic horizon, beyond the 46 billion light-year sphere we can observe, there might be regions of antimatter. If the boundary between a matter domain and an antimatter domain happens to be nearby, cosmologically speaking, then high-energy antinuclei might occasionally reach us from across that boundary. The AMS-2 experiment on the International Space Station is searching for exactly this: anti-helium nuclei arriving from space. Standard astrophysical processes cannot produce anti-helium at any detectable rate. A confirmed detection would be extraordinary evidence for a matter-antimatter domain structure in the universe. As of current data, there are a small handful of candidate events. The significance remains disputed. Now, let's talk about dark matter, not its nature, which is unknown, but its history, which can be traced with some precision. We know dark matter exists. Fritz Zwicky deduced in 1937 that the galaxies in the Coma cluster were moving far too fast for the visible mass to hold them. Vera Rubin and Kent Ford measured in the 1970s that spiral galaxies rotate with flat curves. The outer stars orbit at the same speed as the inner ones, which requires an invisible mass halo extending far beyond the visible disk. Every other probe of gravity on cosmic scales, gravitational lensing, X-ray emission from hot cluster gas, the acoustic oscillations imprinted in the cosmic microwave background, tells the same story. There is roughly 5 times more dark matter than ordinary matter in the universe. What it is remains one of the greatest open questions in physics. We know what it isn't. It is not ordinary baryonic matter, gas, dust, dim stars, black holes, because the primordial nucleosynthesis calculations we will discuss shortly constrain the total amount of baryonic matter, and it falls short of the measured total by exactly the dark matter fraction. It is not made of neutrinos because neutrinos move too fast in the early universe and would have washed out the small-scale density fluctuations that seeds became galaxies. Yet those structures exist in abundance. It does not interact electromagnetically, or we would see it absorbing and emitting light. It interacts gravitationally and possibly through the weak nuclear force and through nothing else we have measured. The candidate with the most theoretical support is the weakly interacting massive particle, the WIMP. The argument for WIMPs is not just negative evidence, but a positive calculation. If dark matter consists of particles that interact through the weak force, with masses between 10 and 1,000 proton masses, then the freeze-out calculation produces a present-day dark matter abundance that matches observations to within a factor of a few. This matching is not forced. You don't tune any parameters. You simply ask, given weak force cross-sections and particle masses in the natural range suggested by particle physics, when does the annihilation rate drop below the expansion rate? The answer comes out right. Physicists call this the WIMP miracle, which is perhaps too strong a word, but the coincidence is striking. The freeze-out works as follows. In the early universe, dark matter particles were constantly annihilating into standard model particles and being recreated from them in thermal equilibrium. As the universe cooled, the equilibrium number density fell exponentially. There was less thermal energy available to create massive dark matter pairs. The annihilation products were still present, but the reverse process, recreating dark matter, became exponentially suppressed. For a time, the total number of dark matter particles fell rapidly. Then the expansion stretched the dark matter particles far enough apart that they could no longer find each other. Annihilation became negligible. The number froze. The relic density we observe today is the legacy of that freezing. If WIMPs exist, they should occasionally scatter off atomic nuclei in underground detectors, depositing a tiny pulse of energy that can be measured. Experiments have been searching for this signal for 30 years. Lux and Panda X in liquid xenon, CDMs in germanium and silicon xenon 1T, and its successor X-xenon T, ever larger, ever colder, ever deeper underground, ever more sensitive. The sensitivity of these experiments has improved by many orders of magnitude. They have found nothing. The simplest WIMP parameter space, the region that seemed most natural from particle physics, has been largely excluded. WIMPs may still exist in corners of parameter space, not yet probed, but the WIMP miracle is looking somewhat less miraculous than it once did. The leading alternative candidate is the axion, a very light particle with a mass perhaps 1 billion times smaller than the electron, proposed in the late 1970s to solve an unrelated problem in quantum chromodynamics. Axions would have been produced in enormous quantities in the early universe, not through thermal processes, but through a coherent oscillation of a field, and they would behave as cold dark matter despite their tiny mass. Axion detection requires completely different experimental approaches. Sensitive microwave cavities in strong magnetic fields that could convert a dark matter axion into a detectable photon. Experiments like ADMX and Haystack are beginning to probe the relevant parameter space. The next decade of axion experiments may be as decisive as the WIMP searches of the past 30 years. There are other possibilities: primordial black holes formed in the early universe before nucleosynthesis, which would count as dark matter without being any new species of particle. Sterile neutrinos produced through mixing with ordinary neutrinos, various other exotic proposals. The particle physics of dark matter is genuinely unknown, and the answer, when it comes, will be one of the great discoveries of physics. 1 second after the Big Bang, the temperature was around 10 billion degrees, or a few million electron volts. At this temperature, neutrinos were central actors. Neutrinos are the most numerous massive particles in the universe. For every proton or neutron, there are approximately 300 million neutrinos, 100 million of each of the 3 species. They are extraordinarily weakly interacting. A light year of solid lead would stop only about half the neutrinos passing through it. The Sun produces neutrinos in vast quantities in its core, and they pass through the entire body of the Sun in essentially the time it takes light to cross its radius. Right now, 65 billion solar neutrinos pass through every square centimeter of your body every second, unimpeded. But in the early universe, at temperatures of millions of electron volts, the density was so extreme that even neutrinos were trapped. The mean free path, the average distance a neutrino travels before interacting with something, was far shorter than the Hubble radius, the effective size of the observable universe at that moment. Neutrinos were in full thermal equilibrium with the photon bath, with electrons and positrons, with everything. Then the temperature dropped below approximately 1.5 million electron volts. The weak interaction rate, the rate per neutrino at which interactions occurred fell below the Hubble expansion rate. Once the expansion rate exceeds the interaction rate, the universe is expanding too fast for equilibrium to be maintained. Neutrinos decoupled. They ceased interacting with the rest of the universe and began to propagate freely through space, carrying with them a snapshot of the thermal distribution they had at the moment of decoupling. These are the cosmic background neutrinos, and they have been flying freely ever since, for 13.5 billion years, through the formation of all structure, through the death and birth of countless stellar generations, impervious to it all. Shortly after neutrino decoupling, a separate event transformed the photon bath. As the temperature dropped below the electron rest mass, 500,000 electron volts, electrons and positrons began to annihilate faster than photon collisions could recreate them. The electron-positron pairs nearly vanished, and their energy went entirely into the photon gas. The photon bath was heated relative to what it would have been from expansion alone. The neutrinos had already decoupled. They received none of this heating. The result is that our universe today has two background radiation temperatures: the cosmic microwave background, the photons that have been propagating freely since the universe became transparent to light at a redshift of about 1,000, roughly 400,000 years after the Big Bang, has a temperature of 2.726 degrees above absolute zero. The cosmic neutrino background has a temperature of 1.945 degrees. The ratio between these temperatures, the factor by which the photon bath was heated relative to the neutrino background, can be calculated exactly from thermodynamics, and it matches the measured photon to neutrino temperature ratio precisely. The cosmic neutrino background has never been directly detected. The neutrinos have too little energy and interact too weakly. A direct detection would require a target with extraordinary mass or a detector of extraordinary sensitivity. Several proposals have been discussed. None has succeeded. But the neutrino background is not merely a theoretical prediction. It leaves measurable imprints on the cosmic microwave background through its effect on the expansion rate, and measurements of CMB fluctuations are sensitive to the total energy density in relativistic species at the time of last scattering. The data is consistent with exactly 3 neutrino species contributing, and inconsistent with either 2 or 4, at statistically significant levels. Neutrinos carry another constraint that comes from cosmology rather than particle physics. Neutrinos are massive. We know this from oscillation experiments, which show that a neutrino produced as one flavor periodically converts into another as it propagates, a quantum mechanical phenomenon that requires the 3 neutrino mass eigenstates to be distinct and non-zero. But the masses are extremely small. The cosmic large-scale structure encodes the neutrino masses. Massive neutrinos move fast in the early universe, streaming freely across large distances and suppressing the growth of density perturbations below a characteristic free-streaming length. The more massive the neutrinos, the more they suppress small-scale structure. Surveys of the large-scale distribution of galaxies find that the observed power spectrum matches predictions with small to zero neutrino masses and deviates increasingly from predictions as the masses are raised. The current cosmological upper bound on the sum of all 3 neutrino masses is around 0.12 electron volts, less than 1 part in 4 million of the proton mass. This is by far the most precise constraint on neutrino masses available from any source, more constraining than any laboratory endpoint measurement. The neutrino sector also contains one of cosmology's current puzzles, the lithium problem. Big Bang nucleosynthesis predicts a specific abundance of lithium-7 in primordial gas that has never been enriched by stars. The observed abundance in the most metal-poor stars, which serve as proxies for primordial composition, is about 3 times lower than predicted. This discrepancy has persisted for decades despite extensive checking of both the nuclear reaction rates and the stellar observations. Either the nuclear physics is wrong at the level of a currently undetected reaction that destroys lithium, or the stellar measurements are systematically biased by some physical process inside old stars, Or there is new physics, perhaps involving a light particle that was produced alongside neutrinos and diluted the baryon to photon ratio slightly. The lithium problem may be mundane, or it may be a hint. At present, we don't know. Now we reach the neutrons. At temperatures well above 10 million electron volts, neutrons and protons were in thermal equilibrium. They converted freely into each other through the weak interaction. A proton absorbs an electron and emits an electron neutrino, becoming a neutron. A neutron absorbs a positron and emits an electron antineutrino, becoming a proton. The reverse reactions ran equally fast. The ratio of neutrons to protons at any moment was determined by a simple thermodynamic formula involving the mass difference between neutrons and protons and the temperature. When the temperature is much larger than the mass difference, the equilibrium ratio approaches 1:1. The neutron is heavier than the proton by 1.293 million electron volts, a tiny difference, less than 0.14% of the proton mass. But in the early universe, this small number mattered enormously. As the temperature fell below 10 million electron volts, the Boltzmann suppression of the heavier particle became significant. There were thermodynamically fewer neutrons than protons by an amount that grew as the temperature fell. The universe was consuming its neutrons. Then came freeze-out. At around 1 million electron volts, the weak interaction rate fell below the Hubble rate. Neutrons and protons stopped interconverting. The ratio was fixed at approximately 1 neutron for every 6 to 7 protons, a number that can be calculated precisely from the weak interaction cross-section, the proton-neutron mass difference, and the neutron lifetime, all of which are measured in the laboratory. This ratio is not the final one. Free neutrons are unstable. A neutron sitting by itself decays into a proton, an electron, and an antineutrino with a half-life of about 880 seconds, about 14.5 minutes. Every second of delay before neutrons are locked into stable nuclei is a second of neutron decay. The universe does not give neutrons much time to wait. After freeze-out at about 1 second, the clock is ticking. There is, however, an obstacle that delays nucleosynthesis. The first nuclear bond is deuterium, 1 proton and 1 neutron fused together. But deuterium is fragile. It can be easily broken apart by the energetic photons flooding the early universe. As long as the temperature is high enough that a significant fraction of photons have energies above the deuterium binding energy of 2.2 million electron volts, deuterium is photodissociated as fast as it forms. The buildup of heavier nuclei is blocked. This is called the deuterium bottleneck. The bottleneck breaks not when the temperature drops below 2.2 million electron volts. It breaks considerably later because there are so many photons per baryon, roughly 2 billion of them, that even the rare photons in the high-energy tail of the thermal distribution are enough to maintain photodissociation until the temperature is well below the binding energy threshold. The universe has to cool to around 100,000 electron volts before deuterium can accumulate. This happens at about 3 minutes of cosmic age. Once deuterium accumulated, the nuclear reactions proceeded in a rapid cascade. Deuterium fused with a proton to make helium-3. 2 deuterium nuclei fused to make either helium-3 plus a neutron or tritium plus a proton. Tritium fused with deuterium to make helium-4 plus a neutron. Helium-3 fused with a neutron to make tritium, which then fused further, multiple pathways, all led to the same destination. Helium-4. Helium-4 was the gravitational attractor of Big Bang nucleosynthesis. Its binding energy per nucleon, 7 million electron volts, is the highest of any light nucleus, making it energetically favorable relative to anything that could be built from it. And there it sat. The nucleosynthesis reaction network ran into a gap. There is no stable nucleus with mass number 5. Helium-4 plus a proton produces unstable lithium-5, which decays back in less than 10 to the minus 22 seconds. Helium-4 plus a neutron produces unstable helium-5. Same problem. To go further required either two helium-4 nuclei making beryllium-8, also unstable, decaying in 10 to the minus 16 seconds, or the simultaneous collision of three helium-4 nuclei making carbon-12 directly. That three-body reaction, the triple alpha process, is what makes carbon inside stars. It happens in red giant cores at temperatures around 100 million degrees, over millions of years of steady burning. The early universe had neither the time nor the density. By the time the deuterium bottleneck broke and helium started forming in earnest, the universe was 3 minutes old and cooling rapidly. The reactions ran for a few minutes at most. Then the temperature fell below the threshold for any significant nuclear reactions. The universe was left with what it had. What it had was roughly 75% hydrogen by mass and 25% helium-4, with a trace of deuterium, a few parts per 100,000 by mass, that didn't fuse all the way, and a trace of lithium-7 at the level of about 1 part per billion. These numbers have been measured. The helium abundance is seen in the emission spectra of metal-poor HII regions, ionized gas clouds in dwarf galaxies that have undergone minimal chemical enrichment from stellar processing. The deuterium abundance is measured in the absorption spectra of ancient quasar sightlines, where intergalactic gas clouds at high redshift imprint absorption features at the deuterium Lyman alpha wavelength, slightly offset from the more abundant hydrogen feature by the isotope shift. Both measurements agree with predictions. The helium fraction is not a free parameter. It encodes the neutron-to-proton ratio at freeze-out, which encodes the weak interaction rate, which encodes the expansion rate at that epoch, which encodes the total energy density, which encodes, among other things, the number of neutrino species. More neutrino species means more energy density at nucleosynthesis, faster expansion, earlier neutron freeze-out, higher neutron fraction, more helium. Each additional neutrino species shifts the helium fraction by about 1 percentage point. The observed helium abundance is inconsistent with 4 neutrino species and consistent with 3. The early universe, through its helium, counted the neutrinos for us, decades before any particle accelerator did. The neutrons almost didn't make it. If the universe had expanded more slowly, if there had been less energy density at freeze-out, the weak interaction would have stayed in equilibrium longer, converting more neutrons to protons, and the final helium abundance would have been lower. If the neutron lifetime were longer, more neutrons would have decayed during the delay before nucleosynthesis, and again less helium. If the baryon-to-photon ratio were higher, the deuterium bottleneck would have broken earlier, less neutron decay would have occurred, and the helium fraction would be higher. The 25% helium we observe is the result of several independent physical constants combining in a specific way. We did not choose them. We inherited them from the universe that existed before us. Before the first second, while the quark-gluon plasma was cooling, a further event of fundamental importance occurred, the quark confinement transition. At roughly 170 million electron volts, the quark-gluon plasma underwent a phase transition into ordinary hadronic matter. The quarks that had been moving quasi-freely in the hot plasma were suddenly permanently bound into hadrons, protons, neutrons, pions, and dozens of more exotic states. This transition is called QCD confinement, and its details are still a subject of active research. Unlike the electroweak transition, which can be studied using perturbation theory, the confinement transition is deeply non-perturbative. The strong force becomes strongest precisely when the coupling is too large for standard expansion techniques to work. It requires numerical simulations on supercomputers, a field called lattice QCD. What we know from those simulations is that the confinement transition in a universe with the physical quark masses we have is not a sharp first-order phase transition, but a smooth crossover. There is no latent heat, no dramatic boundary, just a rapid change in properties over a narrow temperature range. The universe passed through it smoothly. The hadronic matter that emerged consisted overwhelmingly of pions, the lightest hadrons, which quickly decayed and annihilated as the temperature dropped further, leaving behind the baryons and antibaryons. Almost all of those baryons and antibaryons then annihilated too, leaving only the tiny excess from baryogenesis, the 1 part in 10 billion, as the residual matter content. In energy terms, this annihilation was not a catastrophe. Most of the universe's energy had always been in radiation. The matter sector was always a small perturbation on the radiation bath. The annihilation of baryons and antibaryons just added a bit more to the photon gas. The universe barely noticed. Before neutrino decoupling, before neutron freeze-out, before the QCD transition, there was the electroweak phase transition. In modern physics, the vacuum is not empty. It is a quantum field in a specific lowest energy state, and the laws of physics as we observe them are determined by the properties of that state. The vacuum contains, among other things, a background field, the Higgs field, that pervades all of space with a known zero average value. The Higgs field is not a property of any particle. It is a feature of the vacuum itself. And because it's there, certain particles that would otherwise be massless acquire mass by interacting with it. This is the Brout-Englert-Higgs mechanism confirmed experimentally with the discovery of the Higgs boson at CERN in 2012. In the very early universe, at temperatures above roughly 100 electron volts, the situation was different. At high temperatures, the Higgs field's effective potential, the energy landscape that determines the equilibrium value of the field, takes a different shape. The state that minimizes the energy is at zero. The Higgs field fluctuates around zero. No mass is generated, and all particles are massless. The electromagnetic and weak forces are unified into a single electroweak force. The W and Z bosons, the carriers of the weak force, are as massless as the photon. As the temperature dropped through approximately 100 electron volts, the effective potential changed shape. A new minimum appeared, displaced from zero. The Higgs field rolled into this new minimum and settled there. The vacuum snapped into a new, lower symmetry state. The W and Z bosons acquired masses of 80 and 90 proton masses respectively and became extremely short-ranged. They can only propagate over distances of about 10 to the minus 18 meters, which is why the weak force only operates inside atomic nuclei. The photon remained massless and long-ranged. The electromagnetic and weak forces, once unified, became distinct. This electroweak symmetry breaking is one of the pivotal events in the universe's history. Not because it released a lot of energy, the cosmological consequences of the energy released were minor, but because it changed the rules. Before it, particles did not have their present masses. Electrons, quarks, W bosons were all massless. The laws of physics we know are low-temperature laws emergent from a higher symmetry state that existed for the first 10 trillionths of a second. The electroweak transition is also a candidate site for baryogenesis. If the transition was a strongly first-order phase transition, proceeding through the nucleation of bubbles of the new phase expanding into the old, like boiling, then the expanding bubble walls would have provided the out-of-equilibrium environment that Sakharov's third condition requires. The reflections and transmissions of particles off bubble walls, with their CP-violating interactions, could have generated the baryon asymmetry. Whether the transition was actually strongly first-order depends on the shape of the Higgs potential, which the mass of the Higgs boson, discovered to be 125 proton masses, nearly rules out in the minimal standard model. Extensions of the standard model with additional Higgs fields or other new particles can preserve the possibility. This is one reason the precise properties of the Higgs boson are of such cosmological importance. They may contain information about whether the matter in the universe was created at this transition, at even higher temperatures, somewhere around 10 to the 16th electron volts. Though this is uncertain, there may have been a further transition unifying the strong force with the electroweak force. The evidence for this is indirect. When you measure the strengths of the three forces of the Standard Model and extrapolate them to higher energies using the known running of coupling constants, they converge toward a common value at a scale near 10 to the 15th or 16th electron volts. The convergence is not exact in the minimal theory, but becomes precise in supersymmetric extensions. Whether this convergence is meaningful, whether it points to genuine unification, or whether it is a numerical coincidence, is unknown. The energy scale of grand unification is about 1,000,000,000,000 times higher than anything any accelerator will ever reach. What we can say is that if grand unification happened, it also provided the mechanism for proton decay, the slow, improbable process by which a proton converts into a positron and a neutral pion. The proton lifetime predicted by the simplest grand unified theories is around 10 to the 31st years. Experiments have not found it. The current experimental lower bound on the proton lifetime in some decay channels is now above 10 to the 34th years, excluding the simplest models. More complex grand, unified theories survive. The proton appears to be stable, but the search continues in large underground detectors filled with water or liquid argon waiting for a proton to decay, because if it ever does, it will confirm something about physics at an energy scale that no other experiment can reach. What we have traced here is the thermal history of the universe from its first fraction of a second to its first few minutes. A sequence of transitions and freeze-outs, each locking in a physical condition that persists through all subsequent time. The electroweak transition at 100 electron volts determined the masses of all particles and the distinction between electromagnetism and the weak force. The QCD transition at 170 million electron volts confined quarks permanently inside protons and neutrons, transforming a liquid of free color charges into the hadronic matter we know. Baryogenesis, at some temperature we have not yet pinpointed, generated the 1 in 10 billion excess of matter over antimatter that is the reason anything exists at all. Dark matter froze out, its comoving density preserved from that moment to this. Neutrinos decoupled at 1.5 million electron volts and have been propagating freely since, filling all of space at a temperature of 1.95 degrees, undetected and uncounted. The neutron-to-proton ratio froze out at 1 million electron volts, starting the neutron clock ticking toward decay. Nucleosynthesis began at 100,000 electron volts and ended at 3 minutes, writing the first line of the periodic table in hydrogen, helium, deuterium, and a trace of lithium. These events are not independent. They are one continuous physical process, each step setting the initial conditions for the next. Change the neutron lifetime, and the neutron fraction at nucleosynthesis changes, and the helium abundance changes. Change the number of neutrino species, and the expansion rate at nucleosynthesis changes, and the helium abundance changes. Change the matter-antimatter asymmetry, and there is no matter. Change the dark matter cross-section, and the freeze-out temperature shifts, and the dark matter density is different, and the gravitational structure of the universe is different, and the first galaxies form differently. Every link in this chain leads to every other. Consider what it means that we can even ask these questions. The physics of the first 3 minutes happened at temperatures and densities that are, in some regimes, entirely beyond the reach of any experiment we could build. The quark-gluon plasma at microseconds after the Big Bang was at energies briefly accessible to heavy ion colliders, but the temperatures relevant to baryogenesis may never be replicated in a laboratory. And yet we are not completely in the dark. The fossil record of those early events, the helium fraction, the deuterium abundance, the CMB fluctuation spectrum, the large-scale structure, provides constraints that rule out entire classes of theories and sharpen our understanding in ways that would have seemed impossible a generation ago. It is worth stepping back and asking, why do we believe any of this? None of us was there, No instrument recorded the first second. The evidence is indirect, spread across multiple observational programs requiring careful modeling to extract. The evidence is also overwhelming, and it comes from directions independent enough that a conspiracy of systematic errors cannot explain away the agreement. The cosmic microwave background is a direct photograph of the universe at 380,000 years, when it first became transparent. Its temperature across the sky is uniform to 1 part in 100,000. The residue of the primordial plasma, smoothed by inflation, seeded with fluctuations that grew into galaxies. The CMB spectrum is the most perfect blackbody ever measured. Any distortion from a blackbody shape would indicate energy injection into the photon bath at some epoch, and the measurements show none above an exquisitely small upper bound. The fluctuation pattern in the CMB is now mapped in extraordinary detail by the Planck satellite. It encodes the baryon density, the dark matter density, the number of relativistic species at last scattering, the Hubble constant, and the spatial geometry, all measured simultaneously, all consistent with independent determinations by other means. The primordial abundances of helium, deuterium, and lithium are written into the oldest objects in the universe. The helium fraction in metal-poor HII regions, nebulae in dwarf galaxies that have processed the least stellar material, is measured by comparing hydrogen and helium emission line strengths. The deuterium abundance is measured in high redshift quasar absorption systems, where clouds of pristine intergalactic gas leave absorption features at the wavelengths of hydrogen and deuterium Lyman alpha lines. Both quantities are sensitive to the baryon to photon ratio, and both independently give the same value that the CMB acoustic oscillations also imply. 3 independent measurements spanning different objects, different epochs, different physical processes, returning the same number. That is not luck. That is the universe confirming its own history. The large-scale structure of the universe is the grown-up version of the density fluctuations that inflation seeded and that the hot plasma of the first 400,000 years processed. The acoustic oscillations in that plasma sound waves, driven by the pressure of radiation, left a characteristic imprint at a specific length scale when the plasma became transparent and the oscillations froze. That length scale is visible in the CMB as a characteristic angular size. The same length scale projected onto the present-day universe using known expansion history should appear as a preferred separation between galaxies. It does. The baryon acoustic oscillation feature has been detected in galaxy surveys covering billions of light-years at exactly the predicted scale to within measurement errors. The early universe and the late universe are telling the same story. These measurements have a further property that makes them particularly powerful. They are over-constrained. The model has fewer free parameters than the number of independent observations used to test it. A model with as many parameters as data points can always fit the data. It's trivially flexible. The concordance cosmological model, inflation, cold dark matter, baryons at the nucleosynthesis abundance, a cosmological constant, fits dozens of independent datasets with a handful of parameters. When a model of that simplicity describes that range of phenomena, the failure modes become very narrow and confidence in the underlying physics becomes substantial. The universe is 13.8 billion years old. The period we have been discussing lasted 3 minutes. In those 3 minutes, the universe cooled through temperatures no laboratory has achieved and no theory has fully described, through phase transitions that redefined the laws of physics we observe today, through a matter-antimatter asymmetry we do not yet understand, through a sequence of freeze-outs that preserved populations of particles still flying through space right now. Everything that followed was a working out of those initial conditions. The formation of atoms at 380,000 years, the birth of the first stars at 100 million years, the synthesis of carbon and oxygen and iron in stellar cores over billions of years, the scattering of those elements into space by supernovae, the collapse of enriched gas clouds into new generations of stars and planets. The long, slow emergence of chemistry, of replicating molecules, of something that could process information, of everything that can look up at the night sky and ask how this came to be. There is a temptation to feel that this story diminishes us, that knowing we are made of atoms that assembled themselves through impersonal physical processes somehow makes us less significant. The opposite conclusion seems more defensible. The fact that the laws of physics operating in a plasma at 10 billion degrees are the same laws you can write down in a laboratory today, that they are consistent, that they have not changed, that they allow us to look backward 13 billion years and reconstruct what happened with quantitative precision, is not a trivial fact about nature. It could have been otherwise. The laws could have been time-dependent. The physics of the first second could have left no recoverable trace, but it left its fingerprints on every hydrogen atom, every helium nucleus, every photon in the cosmic microwave background, every neutrino streaming through your body at this moment. We know the temperature of the universe at 1 second because the universe kept the receipt. That is not something we could have assumed. It is something we discovered, and discovering it required centuries of physics, decades of observational cosmology, enormous telescopes, particle accelerators, satellite missions, thousands of scientists working on fragments of a puzzle none of them could see in full. The picture that emerged from all of that work is not complete. We do not know what dark matter is. We do not know how baryogenesis occurred. We do not know what happens at energies above the electroweak scale. The first fraction of a second is not fully understood, but we understand the first 3 minutes well enough to predict the composition of the universe to a few % accuracy, to count the neutrino species from the helium fraction, to trace the present large-scale structure back to quantum fluctuations stretched by inflation to cosmic scales. We know in quantitative detail how the universe went from a temperature of 10 billion degrees to the structured, cooled, expanding, accelerating cosmos we inhabit today. We did not build a time machine. We built physics. And it turned out that the universe is made of physics all the way down, that the same equations that describe a proton also describe the first 3 minutes, and that the universe has been kind enough and consistent enough to let us read its history in the sky.